Night settles over a high desert plateau, the air so clear it feels newly made. Above the basalt horizon, the Milky Way unfurls like a river of crushed ice, each shimmer a sun older than our species. At first glance, the cosmos appears honest. What glitters is what matters. What is dark is simply empty. Yet aim a telescope at a pinwheel galaxy, and numbers begin to disagree with eyes. Stars at its rim orbit as swiftly as those near the hub, racing along tracks that visible gravity cannot reinforce. It is as though an unseen orchestra section plays fortissimo, driving the dance while refusing the spotlight. Slide the viewfinder towards two colliding clusters, the bullet cluster, where pastel X-ray clouds of hot gas lag behind the collision while gravity's grip races ahead, mapped by faint distortions in background starlight. Here, mass and light divorce with startling clarity. The heaviest actor wears an invisibility cloak. And while astronomers pondered that hidden pull, another puzzle drifts across the stage. Supernova, stellar detonations that should dim in a steady rhythm, appear to faint for their distances, signaling that space itself is stretching faster every epoch. As though an intangible wind were pushing galaxies apart with patient insistence. Together, these clues scrawl a cosmic graffiti. Something unseen binds galaxies. Something even more mysterious pries them away from each other. One tugs without shining, the other pushes without touching. Their combined dominion approaches 95% of the universe's energy budget, leaving all stars, planets, and poems to share the remaining sliver. We have given them tentative names. Dark matter for the hidden mass, dark energy for the silent shove. But the labels are confession, not comprehension. Placeholders marking the edge of knowledge. Yet ignorance can be generous. It invites wonder, humility, and the thrill of pursuit. Tonight we will follow the faint fingerprints of darkness, from Vera Rubin's quiet rotation curves to the ghostly lensing maps that reveal mass where no telescope sees light. From the acoustic ripples frozen in the cosmic microwave glow to the Type Ia flashbulbs that first betrayed an accelerating sky. We will watch supercomputers grow galaxies on invisible scaffolds, descend into underground caverns where tanks of liquid xenon wait for the gentlest knock, and peer ahead to missions that will weigh the cosmos with gravitational waves and crimson-shifted hydrogen mist. Our journey is not solely scientific, it is also personal. Every breath, every childhood memory, every act of love unfolds within a universe governed by entities we have never directly beheld. To understand them is to understand the home that cradles us. So let the desert night deepen. Let the silence sharpen the stars. And join me in listening for the music beneath the darkness. For in that music lies a double riddle. What invisible hand grips the galaxies? And what unseen tide carries them apart? The answers, still unsigned, wait somewhere between the starlight and the shadows. A winter night in the Arizona desert. Thin, sparkling air, the whir of an old spectrograph. And Vera Rubin, pressing her eye to the guiderscope, one by one, she charted the Doppler shifts of stars wheeling through the Andromeda spiral, expecting to see the graceful Keplerian taper Newton would have predicted. Stars near the hub racing, those in the outskirts ambling. Instead, the curve refused to bend. Far-flung stars tore around the disk at the same breakneck speed as stars near the core, as though some unseen hand had tightened the whole galaxy to a single rumbling wheel. Night after night, the pattern repeated. NGC 2403, M33, M101. Every luminous pinwheel pinned to a flat velocity plateau, out up the glow of gas and stars, and their combined gravity was too meager by a factor of 6 to hold the rims in check. By classical reckoning, spiral arms should fray like straw in a gale, flinging stars into intergalactic dark. Yet the galaxies endured, serene and self-contained. Rubin's colleagues searched for mundane answers. Hidden clouds of cold hydrogen, swarms of brown dwarfs, observational error. None could pay the missing mass. The simplest explanation, unsettling in its simplicity, was that halos of invisible matter, vast transparent cocoons, enclosed each galaxy, contributing gravity and nothing else. Today, every child with a modest backyard telescope can trace those same curves, mapping the tug of an entity that neither shines nor scatters light. The lesson stands luminous in its absence. Galaxies spin on the strength of matter we cannot see. If rotating galaxies hinted at shadowy mass, the bullet cluster shouted. 2 titanic galaxy clusters, each 1,000 trillion suns in heft, met head-on some 3.8 billion years ago, passing through each other like spectral juggernauts. Chandra's X-ray eyes revealed the aftermath first, a bow-shock plume of incandescent gas, pink and turbulent, slowed and crumpled by the collision. But when astronomers overlaid a weak lensing map, subtle distortion of background galaxies by gravity, its deepest wells of mass were not draped over the glowing gas at all. They lay ahead of it, like blue ghosts marching through a battlefield unscathed. No tweak of Newton's inverse square law could conjure 2 separate centers of gravity where ordinary matter showed only one. Modified gravity might explain flat rotation curves under special circumstances. It could not split mass from light in this cosmic smash-up. What passed unimpeded through the wreck was something immune to drag and radiation alike, contributing most of the cluster's heft, while the luminous gas lagged behind. Follow-up collisions, El Gordo's fiery mashup, the sausage cluster's elongated scar repeat the spectacle. Hot baryonic matter slowed by shockwaves, invisible mass surging onward. Each scene drives the same verdict deeper. Gravity's dominant player carries no charge, no glow, no heat, only pull. Here, across millions of light years, and at temperatures hotter than stellar cores, the cosmos performs a decisive experiment we could never stage on Earth. Matter, we can see, separates cleanly from matter, we cannot. Leaving gravity to choose its favorite dance partner, and it chooses the dark. Step back in time, not by centuries, but by 13 billion years. The cosmos resembles a hot fog of light and plasma, as even the densest stars today could not imagine. When that fog finally thinned, the first light able to travel freely went sprinting in every direction. We still bathe in its afterglow, and astronomers call it the cosmic microwave background, or CMB, a faint radio haze that fills every inch of sky. Zoom in on that haze and you notice it is stippled, ever so slightly, with warm and cool blotches. Those blotches record sound waves, pressure ripples that once rang through the primeval gas. Think of a cosmic drum. Gravity pulled matter inward, light pressure shoved it back, and the push and pull left a subtle fingerprint. When satellites like Planck and WMAP measured that pattern, they extracted a kind of barcode, peaks and valleys telling how big each ripple grew before the fog cleared. Here lies the surprise. The location of the first peak says most of the universe's mass must have gathered into lumpy knots. The second and third peaks answer, but only a small slice of that mass can be the ordinary atoms that make people, planets, or starlight. Run the numbers and you find ordinary matter accounts for about 1/6 of what gravity demanded. The remaining 85% must be something quieter, something that felt gravity but ignored light entirely. So the oldest light we possess, rather than revealing everything, instead whispers a riddle. Most of what shaped those ripples never glowed at all. Einstein once compared gravity to a bend in the fabric of space-time, and nowhere is that bend clearer than in the sky's ghostly mirages. Point a powerful telescope at a distant quasar, an ancient beacon billions of light years away, and sometimes you see not one point of light but 2, 4, or even a perfect ring. There is no glass lens floating in the void. Instead, a hidden mass in the foreground has curved space itself, steering the quasar's light into multiple paths. Astronomers call these apparitions gravitational lenses. In many cases, the foreground galaxy or cluster is far too light on paper to create the lens we observe. It is like finding a child's magnifying glass, turning street lamps into searchlights. Detailed maps made with a technique called weak lensing, which measures tiny coherent stretches in the shapes of thousands of background galaxies, show broad halos of gravity that extend well beyond the visible stars and gas. Whole ghost halos hang around clusters, massive enough to warp starlight, yet transparent as air. Even on smaller scales, single stars amplify distant planets by microlensing, producing telltale brightening that detectors in Chile and New Zealand catch a few times each year. Some of these brightness jumps reveal lenses heavier than any lone star could be, hinting at compact clumps of unseen material adrift in the Milky Way. Gravitational lensing is, in effect, the universe's inkblot test. Light bends. We read the pattern, and invisible matter steps into view by the shadow it casts on geometry itself. Together with the CMB's ancient barcode and Rubin's spinning galaxies, these arcs and rings form a chorus, each voice different, the song identical. There is more out there than meets the eye. Gather every clue we have. Rubin's steadfast stars, the CMB's primordial barcode, clusters colliding like ghosts, and quasar light bent into cosmic necklaces, and lay them side by side. Each points to an unseen scaffolding, but none yet reveals its shape. To picture that shape, astronomers turn to the largest laboratory we possess. The universe itself, replayed inside a supercomputer. A simulation begins modestly, with a smooth fog of dark matter particles and a whisper of primordial ripples. Press start, and gravity does the rest. Dark clumps seed filaments, filaments braid into vast highways, and like dew beating on a spider's web, galaxies light up, only where those invisible strands knot most tightly. When the computation ends, scientists compare the simulated map with real surveys that chart millions of galaxies across billions of light years. The match is stunning. Voids, walls, and clusters align as though the dark lattice were traced directly onto the night. And so, a picture comes into view. Ordinary matter is the frosting, not the cake. The luminous cosmos rides on hidden ridges that dictate where stars will shine, where gas will cool, even where life may one day emerge. The question is no longer whether this silent architect exists, but what it is made of, and how it sculpts such grandeur. In the next part, we will dive into that grand design following the unseen sculptor from the first heartbeat of the universe. To the spiraling cities of galaxies we inhabit today, we'll watch darkness pull the strings and light dance obediently in its wake. Close your eyes and travel back 13.8 billion years. To an age when the universe was not stars and galaxies, but a glowing fog, hotter than the core of any star, and thicker than the heart of any cloud. In that infant plasma, faint sound waves rolled like pulses on a drum. Their crests were only one part in 100,000 higher than their troughs, soft enough that no human ear could ever hear them, yet loud enough to write the opening bars of the cosmic symphony. Ordinary matter, protons, electrons, newborn light was caught in a tight embrace. Radiation tugged it outward, gravity pulled it back, and the two forces traded blows 250,000 times per second. But something else floated in that fog, something immune to light's push. Dark matter. Cold, transparent, and already abundant, felt nothing but gravity's tug. So while photons kept ordinary matter jittering, the unseen mass began falling inward, deepening each ripple into a hidden well. By the time the universe cooled enough for atoms to form, the fog cleared and light escaped, carrying with it a fossil picture of those ripples. The map we now call the cosmic microwave background. Yet the true architects were the invisible wells beneath. From those roots, filaments of dark matter thickened, and in their valleys future galaxies would one day ignite. The lesson is quiet, but profound. The first structures were laid not by starlight, but by darkness. Next, we'll watch computers rewind and fast-forward this hidden history, revealing the foam-like scaffold on which all galaxies hang. Step into a chilled data hall where blinking lights replace starlight and processors hum like distant cicadas. Here, supercomputers play the universe in fast motion. Feed them simple ingredients: gravity, the measured amount of dark matter, the faint ripples we met a moment ago, and press evolve. What begins as a faint fog of particles quickly stretches into gossamer threads. Nodes thicken into knots. Knots merge into titanic hubs. Between them, vast voids balloon like soap bubbles. This is the cosmic web, a foam hundreds of millions of light years across, yet as delicate as frost on glass. And the stunning truth is that the simulation needs no stars, no supernova, no chemistry to craft this scaffold. Gravity pulling on invisible mass is enough. The dark matter streams together, slowing only where filaments cross. Ordinary matter allowed into the program later merely flows downhill, lighting the junctions like neon tracing a city grid at night. Fly through one of these digital universes and the view feels eerily familiar. A spiral of threads, not unlike neurons in a human brain or roots beneath an ancient tree. Rotate the camera, and patterns echo across scales. Small knots orbit larger hubs. Narrow bridges feed them both. The correspondence with real sky surveys is so striking that astronomers now use these virtual webs as laboratories, tweaking the amount or temperature of dark matter until the simulation's foam matches telescope charts. And yet, in the corners where the code falters, where dwarf galaxies misbehave or spiral arms twist too soon, wait clues to physics we do not yet know. For if gravity and darkness alone can paint most of the canvas, the imperfections hint at finer brushes still missing from our kit. In the next chapter, we'll watch bright matter fall into these invisible valleys, discovering how stars, spirals, and supernova merely gild the skeleton built by dark matter's silent hand. Picture a dark matter halo as a vast but unseen mountain range. It rises in silence, crag upon crag, until gravity deepens its valleys so far that even lightless particles slow their drift. Into those invisible basins, ordinary matter, gas laced with the first atoms, begins to rain. At tens of thousands of degrees, the gas is restless, but as it tumbles, it sheds heat the way a runner exhales steam. Cooled, it pools at the center, spins and flattens into a luminous disk. Switch on the cosmic lights and a spiral galaxy appears, its starry arms tracing the skeleton beneath. Yet the glow does not simply settle, it converses with its dark foundation. When newborn stars detonate as supernova, they hurl gas outward like ash from a campfire, momentarily thinning the spiral arms. Supermassive black holes and galactic cores can do the same, launching jets that stir the surrounding halo and quench future starbirth. In quiet suburbs of the universe, where halos grow steadily, these heated cycles leave the disk intact. In grand design spirals, such as our Milky Way, emerge. Where the dance is rougher, two halos collide head-on, or several jostle in a swarm, the disk shatters into streams. Stars scramble, gas shocks and heats, and the system relaxes into a bloated sphere, an elliptical galaxy, glowing like a cosmic ember. Astronomers now replay these dramas in supercomputer theaters, tuning feedback from supernova and black holes until virtual galaxies sparkle and puff in the same ratios telescopes reveal. So when you gaze at a whirlpool of starlight, remember, you are seeing only the frost along a hidden spine, sculpted by gravity's quiet architect, dark matter. But even master sculptors leave imperfections, and in the smallest corners of the sky, those flaws may expose secrets we are still struggling to decode. Zoom far inside a computer simulation of cold dark matter, and you find halos within halos. A city of skyscrapers surrounded by suburbs, each suburb orbited by villages. The numbers are breathtaking. Thousands of small clumps should twinkle around every big galaxy. Yet when astronomers sweep the real sky with giant telescopes, they find only a few dozen faint dwarfs circling the Milky Way. This missing satellite's gap is the first whisper that our cosmic blueprint may need fine print. Look even closer. Simulations predict that dark matter density should spike sharply toward each halo's heart, forming a cusp. But surveys of dwarf galaxies show gentle cores, densities that level off like the summit of a worn-down hill. And some of the simulated subhalos are so massive that if they existed, they should host bright dwarfs too big to fail at making stars. Yet the sky is quiet where those giants were forecast. Are these cracks in the cold dark matter idea, or is ordinary matter to blame? Supernova winds can blow holes in cusps, puffing cores into existence. Reionization, when the first stars bathed space in ultraviolet light, may have stripped gas from many baby halos before they could sparkle. Others posit warmer or self-interacting dark matter, particles that blur or bump just enough to erase the sharpest peaks. Each puzzle is an invitation. Adjust the particle, refine the feedback, or rethink gravity itself. The cosmos has left us a trail of mismatched footprints. Follow them and we may stumble upon dark matter's true identity, or an altogether new path through physics? To choose between rival answers, we must probe deeper. Weighing particles against paradigms in underground chambers and radio-quiet valleys, that journey begins in the next part. Stand beneath a rural sky, free of city glow, and let the Milky Way arch overhead. A river of starlight steady as ancient myth, it feels complete. Yet every piece of evidence we have gathered, spinning disks, colliding clusters, the infant hiss of the cosmic microwave background insists that most of this river is an invisible current. We can chart its pull, model its architecture, even watch it shepherd galaxies through time, but we have never cupped it in our hands. At this crossroads, two roads diverge into the dark. One says the unseen mass is a new kind of particle, quieter than neutrinos, colder than the cosmic night, lipping through detectors like ghosts through walls. Find that particle, catch its rare collision in a pool of liquid xenon, or listen for its faint conversion to microwave tones in a whispered quiet cavity, and the puzzle locks into place. The equations of gravity remain pristine. Only the ledger of matter grows a new entry. The second road is bolder. Perhaps there is no missing mass at all. Perhaps the law of gravity itself veers from Newton's verse, when the lights grow dim. Tilt the equation just a hair, and galaxies stop demanding dark companions. Some versions, Mont, Teves, emergent gravity reproduce rotation curves with elegant economy, yet struggle against lensing maps and the CMB's acoustic drumbeat. The debate is no longer about numbers. It is about the very grammar of the cosmos. Which path is true? The answer awaits in shafts carved deep beneath mountains, in radio dishes that sip the galaxy's static, in particle beams and precise orbital clocks. We stand on the threshold, poised to weigh the ghost itself or rewrite gravity's oldest poem. In the next part, we descend into those caverns and climb into those towers, pitting particles against paradigms in a bid to illuminate the darkness once and for all. Beneath the Black Hills of South Dakota, an elevator descends through a mile of ancient rock. The rattle of the cage fades. As the air cools, voices drop to a whisper. At the bottom waits something that looks less like a physics experiment, and more like a cathedral to silence, a vat of liquid xenon, cold and clear as melted moonlight. Around it, photomultiplier tubes bloom like mechanical flowers, poised to catch the faintest glimmer imaginable. Here, scientists wait for a trespasser that may never arrive, a weakly interacting massive particle, the WIMP. The idea is disarmingly simple. Take a particle no one has seen, give it the heft of a heavy atom, yet make it so aloof that it slips through planets as starlight slips through glass. Scatter enough of these invisible travelers throughout the cosmos, left over from the Big Bang, and their collective gravity could explain why galaxies spin too fast and clusters cling too tight. But aloofness is a double-edged trait. A WIMP might traverse a light year of lead before striking even once. That is why detectors such as Lux Zeppelin and Xenon burrow deep underground, far from the hail of cosmic rays that pepper Earth's surface. Should a WIMP bump a xenon nucleus, the atom will recoil and flash just a handful of ultraviolet photons, a cosmic knock at the door. Every minute, supercooled electronics sift the darkness for that tiny pulse, amid a sea of radio-quiet calm. Years of watching have yet to reveal a definite signal. Each null result shrinks the range of possible masses and strengths, like tightening a net around an unseen swimmer. Still, optimism lingers in the corridors. After all, nature rarely gives up her secrets on the first polite request. Yet if the universe favors subtlety over muscle, its missing mass could lie not in heavyweight loners, but in countless wisps so light they drift like cosmic pollen. Axions await in the next chamber of our search. Imagine an old-fashioned radio, the kind your grandparents tuned with a brass dial. Instead of music, picture that receiver, listening for a single, pure note, sustained since the dawn of time. This is the essence of an axion haloscope, a resonant copper cavity cooled near absolute zero, shielded from every earthly broadcast, and cradled within a powerful magnet. Its purpose: to catch a whisper from particles so light they make an electron look elephantine. Axions were born on paper in the late 1970s, conjured to mend a flaw in the theory of quarks and gluons. Quite by accident, that same fix endowed the new particle with properties perfect for dark matter. Immense abundance, vanishing shyness toward ordinary matter, and an almost magical ability to transform into a microwave photon. When passing through a magnetic field, like a silent violin string that suddenly resonates inside the right concert hall. Inside the ADMX experiment in Washington State, engineers scanned the cavity's tuning rods micrometer by micrometer, shifting the resonant frequency much as a listener sweeps the FM band. At each setting they linger, hoping that an axion from the galactic halo will drift in, feel the magnetic field, and sing its single-note photon into the detectors. A triumph would appear not as a bright flash but as a hair-thin peak rising from background noise. Evidence that empty space is in fact saturated with invisible melody. Beyond the laboratory, axions may already hint at themselves. Some aging stars cool faster than models predict, as though an extra vent in their fiery furnaces leaks energy in axionic form. Elsewhere, astronomers track the flicker of magnetars, whose colossal fields could coax axions into light right before our telescopes. Between the heavy WIMP and the featherweight axion lies a middle path. Particles warm enough to roam, but light enough to slip through early cosmic webs. Sterile neutrinos shall step onto that path in our next exploration. Neutrinos are the wallflowers of the particle family. Born in nuclear furnaces, streaming through planets as though through mist. For decades we counted 3 kinds, each partner to a charged lepton, all so light they barely register on gravity's ledger. Yet hints from oscillation experiments and reactor anomalies suggest a shy fourth cousin might linger just beyond the spotlight. The sterile neutrino. Unlike its sociable kin, a sterile neutrino would ignore the weak force entirely, conversing only through gravity and the faintest whispers of mixing. Give it a mass of a few kiloelectron volts. Heavier than ordinary neutrinos, far lighter than WIMPsend, it becomes warm dark matter, agile enough to blur the smallest knots in the cosmic web, but still massive enough to sculpt galaxies. Astronomers search for its calling card in X-ray skies. When a sterile neutrino decays, it should emit a photon about half its mass and energy. In 2014, telescopes peering at galaxy clusters spotted an unexpected line near 3.5 keV, a spectral hairline fracture that refused easy explanation. Some hailed it as the sterile neutrino's first public statement. Others cautioned that tangled astrophysics can imitate subtle lines. New missions like EXORISM and Athena will soon sweep the heavens with sharper eyes, testing whether that slender spike is genuine or a mirage. On Earth, beta decay studies tighten the net. Experiments such as Katrine weigh the tail of tritium's energy spectrum, hunting for the tiny kink a sterile neutrino would leave behind. Each null result prunes the parameter space, yet a tantalizing pocket remains. Just large enough for a particle that could ease long-standing puzzles, like the scarcity of dwarf galaxies, or the smooth cores of dark matter halos. But suppose we never catch any particle at all. Could gravity itself be wearing the wrong glasses? In the next section, we revisit bold attempts to tweak the very law Newton and Einstein bequeathed, testing whether darkness is a missing mass or a misread map. Step onto a high plateau at night and trace the arch of the Milky Way. Its spin, Vera Rubin showed us, is too swift for the visible stars to stay bound. One remedy is extra mass the dark matter we've been stalking. Another is more daring. Perhaps gravity grows stronger on galactic scales than our equations allow. Enter modified Newtonian dynamics, or MOND. Proposed by Mordechai Milgram in the early 1980s, MOND tweaks the familiar formula of Newton's second law of motion. When the acceleration drops below a whisper, about a 10/1000th of a meter per second squared. With that single adjustment, the flat rotation curves of spiral galaxies emerge naturally, no unseen matter required. It was an elegant bandage, and for isolated galaxies it fit astonishingly well. Yet galaxies do not live alone. In rich clusters, the MOND correction still falls short. Gravitational lensing around those clusters maps more pull than visible mass plus MOND can muster. Cosmic microwave ripples pose a sterner test. The pattern of peaks demands. A universe whose inertia budget is dominated by something non-baryonic. To keep pace, theorists built relativistic cousins like Thieves and Eric Verlen's emergent gravity, adding fields and phases in hopes of matching lensing in the early universe without dark matter. Thus far, observations from Planck, weak lensing surveys, the bullet cluster keep tipping the scales toward an invisible substance rather than a rewritten rule. Still, modified gravity ideas refuse to vanish. They serve as intellectual probiotics, forcing the community to double-check assumptions and sharpen instruments. The debate has steered fresh observations such as ultra-diffuse galaxies, wide binary stars, gravitational wave propagation that could yet reveal cracks in the orthodox edifice. Whether we chase particles or polish theories, the hunt now widens to every messenger the cosmos offers, from radio pulsars to ripples in space-time. Our next step explores this multi-messenger frontier, where dark matter may finally betray its presence in stereo. For most of scientific history, we studied the universe with one sense: light. Today, new senses are awakening, and each offers a fresh path toward the unseen mass. Think of the cosmos as a grand orchestra. Photons play the violins, but now neutrinos add their subtle woodwinds. Cosmic rays crash like cymbals, and gravitational waves rumble the deepest bass. By hearing the full score, we may at last isolate the quiet theme of dark matter. Begin with pulsar timing arrays, dozens of millisecond pulsars scattered across the Milky Way, each flashing radio beats with atomic clock precision. If a clump of dark matter drifts between Earth and a pulsar, its gravity tugs on spacetime, delaying the pulses by billionths of a second. Combine data from many pulsars, and those minuscule delays line up like dots in a connect the stars puzzle, sketching the mass and motion of the intruder. Projects such as Nanograv and the coming SKA telescope now monitor hundreds of pulsars, turning the galaxy itself into a gravitational detector. Farther afield, merging black holes and neutron stars broadcast gravitational waves. As these waves traverse the cosmic web, they may pass through dark matter halos, picking up tiny phase shifts or lensing distortions. Next-generation observatories such as LISA in space and Einstein telescope on Earth will measure those subtleties, offering a new map of mass unlit by stars. Even high-energy particles join the search. Cosmic ray detectors like AMS ride the International Space Station, counting excess antiprotons that could drip from dark matter annihilations. Neutrino telescopes buried in Antarctic ice hunt upward-going flashes, possible echoes of dark matter decay deep within the sun. What unites these diverse messengers is complementarity. A signal in one channel can be noise. The same signal echoed in two or three becomes a revelation. By weaving radio pulses, space-time ripples, and charged particle showers into a single tapestry, scientists hope to triangulate a shadow that no single eye can see. Yet even if the riddle of dark matter yields, half the cosmic ledger remains unbalanced, mysterious pressure driving space itself to stretch. In the next part, we turn from hidden pull to silent push and meet the enigma called dark energy. Our journey through the dark matter labyrinth has carried us from galaxy rotations to colliding clusters, from xenon vaults beneath mountains to radio beacons scattered across the Milky Way. Each clue, whether a missing satellite, an X-ray whisper, or a pulsar's late heartbeat, tightens the outline of an unseen companion that outweighs every shining star 5-1. Yet even as we refine that portrait, the universe reminds us there is another, deeper mystery at play. Look past the local groups and glittering superclusters, and you find the cosmos itself expanding. No surprise, since Hubble. But measure carefully, and the expansion is not slowing under gravity's grip. It is accelerating, as though all of space inhales a steady, unseen energy. This silent push is not a fringe footnote. It dominates the cosmic budget more decisively than dark matter dominates galaxies. We call it dark energy, but the name is a placeholder, a marker for something we do not yet understand. Where dark matter pulls structures together, dark energy drives them apart. One sculpts the cosmic web, the other stretches the web's frame. They are the twin shadows of modern cosmology, shaping everything, from the size of a child's telescope target to the ultimate fate of time itself. So we pivot to the next chapter. We'll trace the discovery of cosmic acceleration follow baryonic sound waves frozen in the galaxy distribution, and confront the vacuum paradox that pits quantum theory against observation by 120 orders of magnitude. Prepare to meet a force that acts everywhere, on everything, yet offers no handle to grasp. Only the quiet conviction that the universe is still rewriting its own expansion script. Join us in Part 4 as we listen to the supernova that first whispered the news, and feel the subtle tug of a darkness that does not pull, but pushes. On a cold Chilean summit in the late 1990s, two rival teams tilted their telescopes toward the same fragile flicker, a dying star in a galaxy halfway to the horizon of time. Typea supernovae are nature's precision flashbulbs. White-hot, near-identical explosions bright enough to outshine their host galaxies, brief enough to mark an instant on the universe's clock. Measure how fast that flash fades and you know its true wattage. Compare with how faint it looks, and distance falls into your hands like a well-worn map. Night after night, the astronomers gathered light curves, plotting brightness against time, expecting a simple story. The farther the supernova, the dimmer it should appear. In lockstep with a universe coasting under gravity's gentle break. Instead, the distant beacons were even fainter, farther than any coasting model allowed. It was as though the road between us and them had stretched while the light was en route, as though the cosmos had pressed an accelerator no one knew existed. Here was acceleration writ in candlelight. No extra stars, no hidden dust could mimic the effect across dozens of explosions, each in a different direction, each offering the same quiet confession. Space itself is swelling faster with age. The discovery did more than tweak a number. It added a new actor to the cosmic cast, one that pushes rather than pulls, invisible yet in command. So by timing the fade of far-off supernovae, astronomers learned that the universe is not just expanding, it is speeding up, propelled by an unseen pressure that outweighs every galaxy's glow. Long before the first stars kindled, the newborn universe was a glowing fog of plasma. Sound could travel there not through air but through light-coupled matter. Every pressure wave that rang through that early fireball left a spherical imprint, like ripples etched into cooling glass. When the fog thinned and atoms formed, those ripples froze in place at a fixed scale, about 500 million light-years across in today's stretched units. It was eons later, galaxy surveys trace that fossil rhythm. Map a few million galaxies, measure how often pairs sit that magic distance apart, and a subtle swelling appears in the statistics, a whisper of primordial thunder. This standing shell, called a baryon acoustic oscillation, is cosmic masonry. Its size is set by physics so early and so simple that we know the ruler's length to better than 1%. Because the shell's span is fixed, its apparent size at different redshifts reveals how much the universe has expanded since each epoch. Projects like EBOS and the newer DESI have carried this ruler across cosmic history and found the same story the supernovae told. The scale of the universe between then and now has grown faster than gravity alone can explain. No single telescope, no single method, whether candle or ruler, stands isolated. Together they harmonize on a single unsettling note. An unknown energy pervades space, urging every meter to become something more. The ripples of primordial sound embossed on today's galaxy web act as a standard ruler. And they, too, insist that a mysterious agent is stretching the cosmos at an ever-quickening pace, confirmation writ not in starlight, but in the arrangement of galaxies themselves. Hold out your hand and imagine you have removed every grain of matter, every wandering photon. What remains should be nothing at all. Yet Einstein's equations allow this nothing to carry energy, a uniform pressure we label lambda, the cosmological constant. Astronomers measure its density at about 6 protons, mass spread through a cubic meter of space. Scarcely a whisper, but enough, across cosmic volume, to overwhelm gravity's pull. Here's the puzzle. When physicists add up the restless jiggle of quantum fields, the zero-point energy that no vacuum can shed, they do not get a whisper, they get a roar, a value larger than the observed lambda, by a factor written not with zeros, but with exponents. 10 to the power 120, It is the worst numerical mismatch in all of science. A budget sheet off by more cash than atoms in the observable universe. Why is the measured vacuum so gentle when theory predicts a storm? Some suggest a hidden symmetry delicately cancels almost the whole tally, leaving the slight surplus we observe. Others invoke a multiverse lottery. Countless regions with random lambda values, life emerging only where expansion is slow enough for galaxies to form. Ours simply won the existential draw. Neither answer satisfies everyone. Both drive new mathematics, new experiments, new late-night debates in coffee-smelling corridors. The same emptiness that lets light pass through glass carries a faint but unstoppable pressure. Yet our best theories predict a force unimaginably stronger, leaving us with a paradox as gaping as the cosmos itself. Suppose the vacuum's push is not a fixed constant at all, but the breath of a sleepy field, quintessent, rolling ever so slowly down a shallow hill in energy space. In this picture, the field's pressure is described by a single number, W, the ratio of pressure to density. A true cosmological constant has W equals -1. Quintessence nudges that value slightly higher, meaning its strength can wax or wane as the universe ages. Telescopes already probed this possibility by comparing galaxy cluster growth, supernova yardsticks, and the frozen ripples of baryon acoustic oscillations. Observers have narrowed W2 within a few percent of -1, but not exactly on the mark. A gentle deviation could hint that dark energy is evolving, perhaps destined to fade and let gravity slow the expansion after all. The equation can bend the other way too. If future data reveal W dipping below -1, we enter the realm of phantom energy. Here, the vacuum's repulsion strengthens with time. Tens of billions of years hence, the scale factor would diverge toward infinity in a finale called the Big Rip. Long before that ultimate tearing, galaxy clusters, stellar systems, even molecular bonds would succumb, each unstitched in turn by the ever-amplifying stretch. Current uncertainties still leave the door open to each storyline: steady lambda, graceful quintessence, or the catastrophic phantom. Next-generation surveys aim to tighten W's leash, turning whispers in the data into verdicts about destiny. Whether dark energy stays constant, ebbs gently, or swells toward a cosmic undoing depends on a single number, W, and the universe is keeping that final decimal just out of reach for now. Stand on a quiet country road and watch two cyclists pedal side by side. One rider coasts in familiar Newtonian fashion, speed fading under gentle friction. The other impossibly glides faster the farther she travels. Dark energy asks us to believe the cosmos is that second cyclist, propelled by an unseen tailwind. Before trusting the tail, scientists tug at the spokes of gravity itself, testing whether the old bicycle's frame might be bent. In the mountain recesses of Chile, the Dark Energy Survey photographs galaxies by the millions, measuring how their shapes are minutely stretched by gravity's pull. If space today obeys Einstein to the letter, the growth of cosmic structure should trace a precise tempo. But swap Einstein's field equations for a rewrite, perhaps a subtle function of curvature. Or a universe where gravity seeps into a hidden fifth dimension and that tempo drifts. Galaxies form too quickly or too slowly, like dancers missing the beat. Meanwhile, astronomers map redshift space distortions, the slight squashing of galaxy clusters along our line of sight caused by their peculiar motions. Too much squashing and gravity is overeager, too little in something else. Call it a chameleon force. Maybe shouldering the load, even tabletop labs join the hunt. Atom interferometer fountains toss rubidium clouds skyward, timing their falls to a billionth of a second, listening for hints of an extra tug or unexpected slack. Every new survey shrinks the hiding place for modified gravity. So far, the universe hums mostly in tune with general relativity, yet the unexplained acceleration remains, like a haunting refrain that refuses to resolve. If dark energy is a mirage, the only way to reveal it is to shake gravity's foundation and see whether the cosmos wobbles. Imagine hurling a paper boat into a broad river. Even after your hand lets go, the current carries the vessel farther each minute, destined for distant seas you'll never visit. Dark energy is that current writ cosmic, stretches the roots of photons, lengthens the timelines of future explorers, and redraws the very geodesics we once called straight. Voyager 1, racing beyond the heliopause, already feels the stage beneath it subtly widen. In a few trillion years, no matter how long its silent antenna waits, the Milky Way's neighbors will have slipped behind an event horizon of relentless expansion. For any civilization that follows, navigation will mean steering through a universe that grows faster than rocket engines can compensate, and plotting courses across a map whose scale bar lengthens as you read it. In our next chapter, Part 5, Weighing Shadows, we will place instruments, both earthly and orbital, upon this moving ground. We will see how new telescopes, gravitational wave sirens, and quantum sensors aim not just to watch the darkness, but to measure it. Kilogram by elusive kilogram, joule by whisper faint joule. Only then can we ask with any confidence, what destiny awaits a cosmos ruled by forces that hide their faces but command the stage? Dark energy doesn't merely speed the universe, it rewrites every future journey. And our best tools must learn to measure motion on a runway that lengthens beneath our feet. High above the blur of weather and wandering jet streams, a small fleet of silent sentinels circles Earth. Each carries a mirror polished finer than a grain of pollen, and each stares into night with a patience no human eye can match. Euclid, launched by ESA, was built to map the faint warping of starlight, called weak gravitational lensing. Tiny stretches and squeezes in galaxy shapes that betray the presence of dark matter, like fingerprints on glass. Where ground telescopes see the sky through a restless aquarium of air, Euclid drifts in vacuum. No twinkle, no turbulence, just clean geometry written by gravity itself. Soon it will be joined by NASA's Nancy Grace Roman telescope, a wide-angle cousin to Hubble that can capture a patch of sky the size of 50 moons in a single frame. Roman's gift is time. By filming billions of galaxies over years, it will watch the universe's expansion, accelerate, or ease, charting dark energy's pulse with a cosmic stopwatch. And further out, its mirrors still cooling, JWST peers in infrared, the color of cosmic embers. Those long waves slip through dust, revealing dwarf galaxies too dim for earlier surveys. Their numbers and shapes act as a census of how dark matter clumped when the universe was young. Orbit, then, is more than altitude. It is clarity. It's an unobstructed line of sight to the universe's most delicate signatures. Hence, by lifting our eyes above the atmosphere, space telescopes turn the invisible tug of dark matter and the gentle push of dark energy into crisp, measurable patterns. Back on Earth, human ingenuity answers thin air with sheer scale. In the Chilean Andes, the Rubin Observatory rests atop Cerro Pachin. Telescope so wide it could swallow a basketball court. Every 30 seconds, its 3.2 gigapixel camera captures the whole southern sky, building a nightly time-lapse that will span a decade. As galaxies drift just a hair on its sensors, software measures the minute stretching of their images, the signature of dark matter's hidden scaffolding evolving in real time. Half a world away, the square-kilometer array spreads thousands of radio dishes across desert plains. Tuned to the 21-centimeter whisper of hydrogen, it will chart intergalactic gas from the cosmic dawn onward, carving a three-dimensional map of structure formation. Think of it as a CAT scan for the universe. Slice by slice, it reveals how dark matter's gravity gathered ordinary atoms into the first stars. Even traditional optical giants have learned new tricks. Adaptive optics fires lasers into the upper atmosphere, creating artificial guide stars. Computers then bend mirror segments hundreds of times a second, erasing the jitter of air and leaving star images as sharp as those seen from orbit. Add machine learning algorithms that sift petabytes of data for lensed arcs and supernova flares, and mountaintop domes become smart sensors, not just big ones. Together, these ground titans complement their spaceborne cousins. One offers an unblinking movie, the other the color and depth of a cosmic MRI. Giant telescopes on Earth trade altitude for aperture, capturing the evolving dance of dark matter and hydrogen in unprecedented detail. On the 17th of August 2017, two neutron stars, objects so dense a teaspoon would outweigh Everest, spiraled together in the galaxy NGC 4993. LIGO and Virgo felt their final seconds as a rising whoop in spacetime, signal as unmistakable as the chime of a front doorbell. Astronomers call such events standard sirens. Like supernova standard candles, they reveal distance. But through vibration, rather than light. The louder the ring, the nearer the source. And Einstein's equations set the volume precisely. Just 1.7 seconds after the gravitational wave faded, telescopes caught a flash of gamma rays, then an afterglow that blossomed from ultraviolet to radio over days. That flash supplied the missing half of the cosmic coordinate, redshift. Distance from the siren, expansion rate from the glow. Combine them, and you have a fresh measure of how fast the universe is stretching right now. Future mergers will dot that ruler across cosmic time, offering a check on supernova results and a new way to watch dark energy's grip strengthen or slacken. Standard sirens are refreshingly self-calibrating. They need no complicated models of star brightness, no assumptions about galaxy dust. The physics is locked into gravity itself. As LIGO upgrades and the coming Einstein telescope tune their ears, dozens, perhaps hundreds of these cosmic doorbells will ring each year, each one a data point on the graph of universal growth. Gravitational wave sirens let the universe announce its own distance, turning cosmic collisions into talking rulers that chart the tempo of expansion. While telescopes scan the heavens, basement laboratories wage a quieter campaign. One waged in total darkness, shielded from cosmic rays, vibration, even footsteps on a distant sidewalk. Deep inside an old South Dakota gold mine, the Lux Zeppelin detector holds 10 tons of liquid xenon as pure as melted starlight. Should a dark matter particle nudge a xenon nucleus, a faint flash, and a handful of electrons betray the encounter? Months may pass with no spark, but patience is the currency of discovery. Just meters away, another experiment listens for subtler guests. Incoherent elastic neutrino nucleus scattering. Neutrinos ricochet off whole atomic nuclei like ping-pong balls, striking bowling balls. Detecting that tiny recoil fine-tunes our grasp of the weak force and could flag new physics that mimics dark matter's messengers. Even gravity itself is placed under a microscope. Atom interferometers launch clouds of ultra-cold rubidium upward and let Earth's pull bend their quantum wavefronts. Compared to such fountains side by side, and any extra tug, a hidden fifth force linked to dark energy or exotic particles would tip the balance. Similar interferometers now fit on tabletops, their laser lattice acting as rulers a billion times finer than a human hair. And then there are quantum sensors cooled to a hair's breadth above absolute zero. Tiny superconducting loops, called squids, monitor magnetic fields a trillion times weaker than a fridge magnet, ready to flag passing axions or other dark whispers. Buried tanks of xenon, levitated atoms, and superchilled circuits turn earthly laboratories into stealth observatories. Places where the subtlest shiver could reveal the universe's hidden ingredients. Walk into any living room after sunset and you will find a quiet miracle. Laptops, tablets, and phones connected to telescopes half a world away. Through projects like Galaxy Zoo and Backyard Worlds, more than 2 million volunteers have clicked their way through deep sky images, labeling spiral arms, spotting warped rings, and flagging the telltale arcs of hidden gravitational lenses. No supercomputer, however fast, can yet match the human knack for pattern and surprise. A retiree in Manchester once found a lens the experts had missed, its ghostly smear betraying a heavy halo of dark matter 12 billion light-years distant. Yet the data flood is swelling beyond any human army. When the Vera Rubin Observatory begins its 10-year survey, it will stream 20 terabytes of sky each night, enough to fill a hard drive tower taller than a giraffe every month. Machine learning algorithms trained on the hand-labeled treasure from citizen scientists will comb that torrent in real time, flagging subtle shears in galaxy images that reveal dark matter clumps, or the tiny brightness wiggles that hint at a type Ia supernova half a universe away. In this partnership, humans provide intuition, AI provides stamina. Together they will map the hidden mass between galaxies and refine the timeline of cosmic acceleration with a precision no single telescope or single mind could achieve. From kitchen tables to neural networks, the hunt for the unseen has become a team sport where every click teaches a computer to sift the cosmos for shadows. We now possess an arsenal worthy of the mystery. Satellites that photograph space like cartographers, ground telescopes that listen to the hiss of hydrogen across epochs, wave detectors that feel the universe ring, and underground chambers that wait in breath-held silence for a single flash. Add to that the collective curiosity of millions, and the tireless focus of artificial minds, and the invisible begins to take shape. Contours traced in lensing arcs, siren chirps, and atom-scale shivers, yet knowing what is out there is only half the story. The next question is what happens next? Dark matter sculpts today's galaxies, but dark energy scripts tomorrow's sky. Will its silent push stretch space until every star slips from view? Could an unforeseen twist in its character tear atoms apart or relent, letting gravity call the cosmos homeward? In Part 6, Fates Written in Darkness, we will fast forward through billions of years. Following models that hint at heat death, Big Rip, or cosmic rebirth, we will watch the Milky Way merge into a lonely island. Weigh the prospect of dark matter decay and imagine technologies like Dyson spheres. Galaxy hopping that might let future minds thrive against the widening void. Join us as we step beyond measurement into prophecy, tracing the paths our shadow-ruled universe may yet walk. Invisible forces built the heavens we know now. They will decide how long those heavens endure. Imagine standing on a high plateau, watching three rivers diverge toward distant horizons. Cosmologists face a similar fork, but the currents are written in space-time itself. First, the Great Freeze. If dark energy is indeed a cosmological constant pushing with a steady, unchanging pressure, the universe will race outward faster and faster. Galaxies will slide beyond one another's reach. Stars will exhaust their fuel. Black holes will evaporate in quantum whispers. And what remains will be a thin mist of lonely photons, cold, silent, and endlessly expanding. Second, the Big Rip. Should dark energy's pressure grow even a little stronger, physicists label that change with a single number, W, and the fabric of space begins to stretch faster than gravity can mend it. Clusters unravel, solar systems peel apart, planets, and finally, molecules themselves are torn loose. A trillion-degree fever ends everything in a final breathless instant. Third, cosmic bounce. If dark energy one day reverses sign or hidden curvature tips the scales, expansion could slow, halt, and contract. Galaxies would drift back together, temperatures climb, and the universe might collapse into a searing renaissance, perhaps even rebounding into a new Big Bang. We do not yet know which river we follow, but every telescope, every particle detector is a sextant on this journey, measuring tiny shifts in redshift, mapping distant supernova, asking, how fast, how long, which way? Our universe faces three destinies: freeze, tear, or return, and the quiet pressure of dark energy holds the deciding vote. On a clear night, our galaxy feels crowded. Orion's belt, the Andromeda smear, a billion suns spangling the dark. Press the cosmic fast-forward key, and that bustle thins with startling speed. Space itself is swelling. Every distant galaxy already speeds away. In a few trillion years, their light will outrun even photons, slipping beyond an ever-closer event horizon. What remains is our local neighborhood. The Milky Way, merging with Andromeda and a handful of dwarfs to form one swollen spiral, Milkdromeda. Outside that island, nothing new will ever sail in. Future astronomers, perhaps living in glittering habitats orbiting long-lived red dwarfs, will look up and see only their own collective home, adrift in blackness. The cosmic microwave background will have stretched into radio silence. The evidence for a Big Bang will lie beyond any instrument they can build. Time, too, grows provincial. As expansion accelerates, clocks tick differently for regions separated by great voids. Eventually, there is no shared now broad enough to span what once was our observable universe. History itself becomes local lore, written in star streams and fossil photons trapped within Milkdromeda's halo. Yet isolation is not emptiness. Inside this future island, stars will still ignite, planets will still circle, and curiosity will still ask questions. Even if the larger answers lie forever over a widening sea, Cosmic acceleration will leave us marooned on a single galactic island. Proof that the sky's richness is a temporary gift of our epoch. Imagine a city whose skyscrapers look carved from granite, yet over eons crumble grain by grain into dust to find a sea. Some cosmologists wonder whether the unseen scaffolding of the universe, dark matter, might be just as fragile. The leading candidates are famously long-lived, but long-lived need not mean immortal. If a dark matter particle carries even the faintest impulse to transmute, the cosmos itself becomes a slow-motion chemistry set. The numbers are dizzying. A half-life of 10 trillion times the age of Earth would still let a measurable drizzle of decay products seep into space today. Satellites such as Fermilot and AMS comb the sky for extra positrons and gamma rays. Tiny flashes that could be the dying breaths of dark matter halos. Deep underground, detectors like Super Kamiokande listen for neutrino murmurs that might rise as those halos shed mass. The stakes reach far beyond particle physics. Should dark matter slowly evaporate, galaxies would lose the invisible glue that holds their stars in graceful orbits. Spirals could unwind, clusters disperse. And the large-scale web we mapped earlier would dissolve into ever-thinning filaments. Black holes, fed less generously, would slim before quantum evaporation finishes the job. We have not yet caught the culprit in the act. Every claimed excess battles, astrophysical alternatives, pulsars, cosmic rays, statistical flukes. But the search continues, because a single confirmed signal would rewrite our cosmic timetable, turning eternal structure into a passing phase. If dark matter can decay even unimaginably slowly, the universe's bones will one day turn to dust, reshaping the distant future we thought was set in stone. Human curiosity rarely accepts a cosmic forecast at face value. We reach for tools, even when the sky's timeline mocks our own. Faced with an accelerating emptiness, futurists sketch audacious blueprints. Grand designs to gather warmth, preserve memory, perhaps outrun the dark. At the modest end lies the Dyson swarm. Billions of solar collectors orbiting a star, siphoning its light before expansion dims the night. Over millions of years, a civilization could migrate from star to star, building fresh shells as old suns fade, an endless relay powered by fusion's last embers. But acceleration is relentless. Eventually, neighboring galaxies slip past any attainable speed. One proposal counters with galaxy herding. Using gravitational slingshots around stars and black holes, advanced cultures might nudge select dwarf galaxies inward, assembling a bound archipelago before the cosmic tide pulls everything else away. Computer models suggest the energy cost is titanic, yet not forbidden by physics. Ambitious, yes, but ambition is a human constant. Further on the speculative horizon sits vacuum energy mining. Quantum field theory allows, in principle, the extraction of work from the negative pressure sea that fuels dark energy itself. Most concepts collapse under practical scrutiny. They demand machinery of planetary mass or perfect control over space-time metrics. But the idea underscores a deeper truth. Future engineers will treat today's metaphysics as tomorrow's resource catalog. In the end, these thought experiments are less about blueprints than perspective. They remind us that even in a universe racing toward solitude, creativity can widen the path, turning a fate accepted into a challenge engaged. Cosmic acceleration may script an ever lonelier stage, yet imagination drafts counterplots, from harvesting starlight to shepherding galaxies, showing that agency can persist even as the universe slips away. Pause and consider the proportions. For every kilogram of familiar atoms, trees, oceans, our own beating hearts, there are 25 kilograms of dark matter and 70 of dark energy. We move through a cosmos in which the visible is garnish, not entree. That imbalance forces an unsettling question. What do we mean by real when 95% of reality hides from sight? For most of history, real meant tangible, stones underfoot, fire on the hearth. Then came air, germs, radio waves. Realities detected only after instruments extended our senses. Dark matter and dark energy push this progression to its silent extreme. We know them only by influence. Stars whip round unseen mass. Distant supernova fade more than gravity alone can allow. The entities remain invisible, yet their fingerprints are everywhere. Philosophers call this inference to the best explanation, accepting an unseen cause, because every observable path points toward it. Scientists call it humility in data service. The lesson reaches beyond astrophysics. Much of what shapes human lives, trust, culture, consciousness, X's invisibly yet undeniably. In that sense, studying the dark sector is not an escape from the human condition, but a mirror of it. Perhaps future detectors will illuminate the shadows, revealing new particle families or rewriting gravity's script. Or perhaps the darkness will endure. A permanent reminder that knowledge grows outward from islands of certainty into oceans forever beyond our lanterns. Dark matter and dark energy teach us that the most influential parts of existence can be those we never directly see, inviting a broader and humbler definition of reality itself. We have journeyed from galaxies that spin too quickly to supernova that fade too fast, from decaying halos to far future megastructures. Thread by silent thread, the dark sector has revealed itself not as an afterthought, but as the loom upon which cosmic history is woven. Invisible mass sculpted the first stars. Invisible energy now stretches the stage on which those stars perform. In darkness, the universe both begins and quite possibly ends. Yet amid that vast obscurity stands a luminous detail. Understanding has grown. Glass lenses, chilled crystals, and patient mathematics. A small species on a small planet has mapped forces it cannot touch. Each unanswered question, what is a WIMP's true nature? Will the vacuum forever accelerate? It's not a void, but an arrow pointing forward. In the closing moments of this episode, we will step back and listen. We will let Vera Rubin's quiet data, the whispers of distant Type Ia supernova, and the steady pulse of microwave background photons merge into one grand dark symphony. And we will ask what it means for science, for culture, for each individual heartbeat to live in a universe whose dominant ingredients lie forever beyond the eye. Join us for that reflection, where the unseen becomes a source of wonder rather than unease, and where the limits of knowledge mark not an end, but a horizon. Ahead, in our final coda, we'll hear how every sunrise owes its glow to forces hidden from sight, and why that truth makes the cosmos more intimate, not more remote. Step outside after midnight, when the traffic hushes and even the crickets pause between songs. Above you stretches a river of light, Milky Way dusted across black velvet. Yet now you know the picture is incomplete. The stars, the nebulae, the moons that stir poets' ink. Together they account for little more than 5% of all that is. The rest moves invisibly, shaping every orbit, every sunrise, every breath of cosmic history. It was Vera Rubin who first heard the dissonance. Spiral galaxies spinning too quickly, as though gripped by ghostly hands. Decades later, distant supernova added their own off-key note, dimmer than gravity alone could allow. Piece by careful piece, astronomers assembled the score. Dark matter is the deep bass line. Dark energy is the rising swell that carries the melody outward. Instruments as different as liquid xenon vats and spaceborne telescopes now play in concert, each probing a register our eyes cannot reach. And yet listen closely, the darkness does not diminish the music, it enriches it. Just as silence between piano notes gives shape to a sonata, the unseen portions of the universe give context to the scene. We value a candle more when we glimpse the night that surrounds it. We cherish warm company because cold space is vast. Knowledge of the dark sector is a reminder that mystery is not the enemy of meaning. It is the medium in which meaning grows. So when dawn returns and sunlight paints familiar colors on familiar walls, remember what rides upon that light. It travels through halos of unknown particles across a vacuum pushed ever wider by unknown pressure, arriving finally at retinas and minds that can know, even if only in part. In that interplay between the known and the hidden lies both the challenge and the romance of science. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.